what we did. So we discovered it was a metric tensor and considered some examples. This lecture, the title of this lecture, covariant derivative. Which is the idea? So, of course, if we would like to find the equation for gravitational field, as I said, what did I say? The previous lectures. So, what we need, we need to have the operation of derivation. So we need to because as you remember, here I put Laplace equation, and we need to generalize it for curve space. So, and we have in the left part here Laplacian, and Laplacian it means, just a second. Okay, so, and Laplacian, as we understand, this is the second derivative, and we need to find the corresponding operation which works in curve space in any reference system. And now we'll start to work with this, and we will see that the result we also obtain some new mathematical objects which call Christoffel symbols, which is very important because later we will discover that describe curvature of space, we will need additional mathematical object which exactly consist of Christoffel symbols, and which call a Riemann tensor. And after this, we will be ready when we investigate the Riemann tensor. And after this Ricci tensor, we will be ready, in principle, to write equations of the field, the gravitational field. Okay, this is the main goal. And now we, in the first, if we are in the flat space, so this is, as I already said, we can speak about, sometimes it's called Galileo coordinates. And Galileo coordinates, it means, the flat space, it means that G00 equal 1, and G alpha beta equal minus 1, where we have an agreement that when I speak about, when I use the Greek letters, alpha, for example, alpha, beta, it means that we use the index which change from 1 to 3, 1 to 3. So as you can see, I already try to apply everything for four-dimensional space and time. Of course, we can generalize it for any space. It's not important. It just, of course, it can work for arbitrary dimension of space, as I already said before. But I will much more concentrate, because it's we are working exactly with general relativity with four-dimensional space-time. So, and ik equals 0 if I not equal k. Okay, so it means that we are in diagonal, we will have only diagonal elements of the metric tensor. So this is for us is very common coordinate system, reference system, because this is flat space, and for four-dimensional this is Minkowski space. And if we have some differential of the vector, in this case, so if you have differential of the vector, we would like to find it, the vector AI. So what we know that in this case, if this is vector, if we will find differential, it will be also vector. So if we want to find derivative dA I by coordinate dx k, and from the vector AI, so this is vector, and in this case we will obtain tensor. It means that if we will go from one reference system to another reference system, so this will be not changed, so the rules will be the same. When we working with curve coordinate system, I will put in general curved coordinate system or reference system. So in this case, if we have a vector AI, again vector, components of vector, and if we will find differential dA, it will be not vector. And the same if we will find dA I by dx k, it will be not tensor. So it means that it will change in curve coordinate system if we will take the vector and make this operation, and we will see that it will be not transform as a tensor. The transformation formula not correspond to the transformation of tensors. So we can really to prove this if we will look on the let's really prove it and see it. This is really not the vector AI not transform from one coordinate system to another as a tensor. So in this case, let's consider. So we have AI and consider dAI. Okay. So the transformation formula for differential, since the vector, this vector, is a covariant tensor of the first rank, and we know how we can transform in from not prime reference system to prime reference system. Again, we have not prime reference system, and we go to prime reference system. Okay. We will use formula which we obtained before. I even can come back to find it. And you can put, for example, the number of the formula to be, that it will be for you much more convenient to find it. Okay. Okay. Not here, not here. This one. Okay. This one. This is exactly the formula of how to transform a vector from prime reference system to not prime. If you would like to write it otherwise, so you understand how to do it. So using this formula, we will obtain the following. Okay. So I will rewrite here this formula, so I can write that this is x. I can write it full way, dx by dx on A, and after this I think which indexes I need to put. Okay, I need to put here I, and this is a pre-index and summation index, for example, k prime, k prime. Okay, the same I can write, and sometimes again we can use it more convenient case. It's just the point of writing. So k prime, comma, I, a, k prime. This is convenient because we even can see here again the conservation of, as we like to say it, conservation of indexes, because here one, and k prime is a two summation index, which time tada should be double. Okay, so let's see what we will have. Now I want to consider d, a, I. So it means I need to apply, and d, this is, say, normal operation of find differential. So in the first, I will apply it in the to a chi prime. So it means that the first multiplier is the same, but here I put d I k prime, and I apply d to the second one. So it means the first I will put a k prime, d from x k prime I. Which is equal, so this is the same, I, d, a, k prime. And here I will even write with a case which for you much more common to use. So it means that d2 x k prime divide d x I dx a and dx l. So, or you can rewrite it, okay? This is the same plus, I can write it much more short way, so, because this is, will be equal, this is the same, but just much more convenient sometimes, describing x, k prime. And here I put as a comma the first derivative, I, and the second L, the X, L. Okay. Bit here. What we can see? We can see that really derivative differential of this vector is not transformed as a tensor, because this the first part looks really like a transformation of tensor. But we also have this part. I can put here like this. This we happy, this we are not happy. So it means that we can't use it if we would like to build the theory and to use the tensors, which are, as we already discussed, are very important, because if you receive this equation in tensor form in one coordinate system, and it's true in this coordinate system, it means that the same equation will work in another coordinate system. So, and since we want that nature law will be, of course, the same for any reference system or coordinate system, we want to write it in the tensor form. And again, we need to remind that why it became complicated, because when we say any reference system, it's also mean, coordinate system, it also means that we can move freely from flat space to curved space. So, and so we can see that this is not a good, so we need to find the operation which create from tensor, again tensor. Why this is like this, we a little bit later we will consider the geometrical sense of covariant derivation, which we will obtain now. Because when we consider the derivation of the vector, it means that we make a parallel moving of this vector in some point in the vicinity of this vector. Okay, but when we make this parallel moving, it means that the component of this vector, they change not linear way, so it's much more complicated. And for example, if it could be linear dependence of component of the vector, we understand that this summon can disappear, because linear, it means the first derivative, this is constant, and the second, this is zero. And we are in business, so everything is okay, which exactly correspond, for example, for the flat space. But since the change of the component of the vector is much more complicated, if we have a curved reference system, so due to this rotation of the vector, when we make a parallel path, it means that the situation is much more complicated. So this is just a simple explanation why we have this problem. But now we will solve this problem. And the main idea, our goal, let's find a new operation. Please write. Or new derivative, which we will call covariant derivative. Covariant derivative. Covariant derivative we can use some notation that if we have vector I, AI with indexes I, and covariant, it means, so you could see before that if we put one, just a comma, it means a normal derivative. If we will put punto comma, no, it doesn't matter, okay. So it means that this is covariant derivative. Okay. So to find or to build this new operation, this new mathematical operation with the vectors, and later we will see that we can generalize it for the tensor of the arbitrary rank. We will impose, we will apply some request which we would like to put as a property of this operation. So what we want to construct. The first, are you here?
Yes, we are here.
Good. So if you are not in time or don't understand something, please tell me. Again, you can use any language. So, okay, 14, good. So the first property, so what we want? We want that covariant derivative should coincide with partial derivative. Derivative in a Cartesian reference system. Coordinate system, okay. Or we can put in flat space, okay. So this condition, this property, it's understandable because yes, of course, as usual, we need as a limiting case to consider the common situation, normal situation, and even from the point of physics, we understand that the gravitational field, which we can describe, should correspond in the limiting case to Newtonian case. From the point of mathematics and our consideration of any reference system, of any coordinate system, so we understand that it should be also work in flat space. The second condition that covariant derivation is the operation, so mathematical operation. You go for the lunch? Super, I have my lectures now, so I can't join. Buon appetito! So, as you can see, I'm without lunch today. Is the operation which transform tensor. So should transform tensor in tensor, okay? When we go from one reference system, or one coordinate system, for example, prime coordinate system to not prime coordinate system. So we want to finally to obtain the tensor characteristic. So what it means? It means that that the first condition give us such a equivalence that we can write that if we, for example, have I variant derivation k, derivative k, so in Cartesian reference system we can write this is equal I just k. Okay, in Cartesian system. The second property tells us that this object which we obtain apply this operation of covariant derivation. So I will, for example, go from prime reference system to not prime. Prime, k prime, okay? So in this case, we need to use a formula of transformation of the tensor. And this, as we understand, that this is mixed tensor of the second rank. So we need to use the corresponding formula of transformation of the tensor from one reference system to another. If we can find this formula, which we obtained before, we can exactly yes, this one. So this one. We can put here the number for this formula and make a reference to this formula here. So this is exactly what we obtained for the case of the tensor of the second rank with co-contravariant components. Okay, so we will use it now. One index, this is top, so we need to put it here, and the second index bottom, k prime, and in this case I need to put the summation indexes. So I have here, put it here m and here n, and after this I can I need to put indexes here. So here index below I put it here, like this. So just consider as a transformation of tensor. This is tensor, and of course we apply this rule for tensors. Now we will use this one, and instead of ai k, we will put this one. Instead of this one, I will put this one.
I'm so sorry, I miss. What is the main difference between comma and comma with dot?
In the comma, right here, comma, it means that this is normal derivative, normal derivative. Okay, this is just d by dx, as we are usually, which we are used. When we put punta comma, it means that it's a different operation to find derivative, which we now will find. And punta comma, it means that this is covariant derivative, which is different from derivative which we are using in the flat space. And now we will try to find it. But again, so this to be much more formal. So it means this correspond normal. Sorry, normal, like this. Okay, and this is covariant. And covariant satisfy these two conditions. It's understandable now?
Yes, understandable.
Okay, now we will find what is exactly, and we will see that it's really different operation, which of course include normal derivative, but for the special case. So, and now we will put here this condition 1. So it means I will rewrite it. You can rewrite. I'll do like this. So now I can, instead to put here punta comma, point comma, punta it's in Italian. So I put it just this comma due to condition 1. So, and after this, let's see what we will have. So look, I can do this xm, the xn, the xk prime, and d, and you can see now I write just this is here 1, it's just a comma, so I can write this like this. Okay, so I can see this one, this is just a dA m to dx k prime. So just from mathematical analysis, dA m dx n. Okay, do you agree?
Yeah.
Maybe we should have a prime index in last part.
I ask you, are you agree? Do you agree with what I with what I wrote?
Maybe
No,
K.
No,
no.
no. I also not agree. So why I ask? It's just to check that you are sleeping already, or to allow you wake up. So where is the mistake? Please tell me.
In last part where we have dxn, we need to have dx k prime.
Right, bravo. Of course. Okay, so but it's not all. So we need to understand. We need to we need to write everything on this part in prime coordinates. And let's consider such it will help us to see something. Let's consider this derivative dx by dx k prime and a m dx I prime dxm. I just want to consider what is this. So now you will see that will be something interesting. So what is it? This is dam right, dxk prime dxi prime divide dxm. Okay, plus am d by dx k prime, which apply to dx I prime dxn. Oh, I will keep like this. So I can see that this one and this one the same. Okay, so from this I can, instead of this, I will put what I have. So I can write here equal, here equal. So it will be let's me simply, okay, so d x k prime, and here I will write like this, a prime d x m a m minus a m d by d x prime x prime dxm. Okay, please check everything because I can make some stupid mistake.
Maybe AM point left side.
So let's check. Therefore, this one d by dxa dxi dxm am okay, minus am dx d by dx dxi. No, everything looks right. I don't understand what exactly you don't like.
Upper index for I.
Ah,
No, where is? Yes, AM.
okay. Yeah,
In
yeah.
left.
Yeah, right. Okay, yes. Thank you. Yes, of course. Here we should be very careful. Okay, so, and what we can see here, we can see that this is, what is this? This is exactly transformation of a contravariant vector a prime. Okay, so, and I can write that this is equal dA I prime dx k prime minus okay, here I can write a m d 2x I prime, and here I need to remember what is it, so I need to put the x m the x n the x n the x k prime. Oh, you know, I describe it much more, so in principle I put it here as a k prime. Or if I will remind, so because it's not good, because here we have I prime, so here we have a primary coordinate system, but here not prime. So I will use here the again transformation formula. So I mean that I can write that AM equal A J prime XM comma J prime. So again, corresponding to the previous formula for contravariant vector. So you can rewrite all of this, but I can just change because I want to finish on this page. So instead of AM, I will kill AM, and I will put here A, J. Let's use. Okay, it's okay. The XM by the XJ prime. So now we have all three indexes in prime reference system. And just to remind the initial point, which is here. Okay, so we start from this one. So here I will put, this is what we obtain. This is AI prime, K prime. In principle, we could put here, I put here like this, but in principle we can write so what I kill and you repeat, you need to repeat, okay? Doesn't mean that you also make this procedure, because for me it's much more convenient. I'm writing in iPad. So what I need to put here, I think K prime. So
And maybe we can remove also left part where is dxm divided by dx j
no,
prime.
it will be not beautiful, because what we are doing here, it's better to keep it, because this is in one derivation, but this is another derivation, this is multiplier. So it's better to keep it, because otherwise I not come back. So we can write here, because this is inside. So I can after this to rewrite what this the second derivative is from the mathematical analysis. So if I know that x k prime some function of x k not prime, so, and it's understandable, it's inside of this one second derivation, but this is another derivation. Okay, it's understandable. No? Are you here? Somebody here?
Yes, here.
Yes, yes.
Okay, let's write here now the final result. And what we have that better if I will keep it, because otherwise it will be some question. Let's keep it. dxm, dxn, dxn, dx k prime. So finally we have the final expression. So a r prime k prime qual. Just normal derivative plus a, and we have here g prime, and also we have this construction which finally have which we will call the letter gamma. I need to put here also n. So, and this gamma has how much? 3 indexes, 3 free indexes, because other indexes are summation indexes. So upper index I have I prime, and index below I have J prime, K prime. So, and in this case, I can write here that this is gamma. Look here, J prime, K prime, I prime. So this is the expression for covariant derivation. This is covariant derivative of the vector of contravariant vector. Of contravariant vector, which is tensor second rank. So in principle, and this gamma, they called the Christopher symbols. Christopher symbols. Why it's called symbols? Because they are not tensor. We will see it a little bit later. So they are not create the object as a tensor, and they can't transform from one coordinate system to another as a tensor. So now I think So now I would like to tell a little bit about geometrical property of this geometrical sense of this covariant derivative, why we have it, and a little bit I already said. So the point that, for example, if we have just a flat space, as we said, so we have the situation that in the flat space or in Galileo system, we have a situation when if you want to find di, so we just have a xk prime, as you understand, dak prime. So this is just a Cartesian system. But if or for example, this is as I already said, this realize when we have linear dependence of coordinate from prime reference system and not prime reference system, due to the fact that in this case this equals 0. Okay, so in general case, when we have a curved space, so and this is our coordinate line, when we want to find differential of some vector, this component ai, so what we are doing, we can make from one point we can make a parallel move of this vector, and we want to move it. Let's consider that this is, it's of course huge, but this is exactly dxi. Okay, so we move it on some point in vicinity of the vector. What in this case we have? If we make a parallel shift, so it means that we will have a vector, we have an agreement, a vector with the same angle. And let's call it this A class, and of course some change delta I. So the second point is we made the parallel shift. But the second, we just move this vector to the point which is in vicinity of this vector. If we just put, so we can schematically to write it like this, due to the fact that when we move through the coordinate system, which is not orthogonal, so it's a curve, so of course this vector will also rotate. So let's schematically we'll write it here that it will be ai plus dai. So as a result, if we want to find the residual, the difference between these two vectors, which we move in one point, so we move one vector in the point in vicinity of this vector, but by two ways, because in the case when we have a curve, a coordinate system, we can do it by two cases. So from one point we move this parallel shift as a parallel shift, and the second one just we move along of the coordinate system. And the result we can write the differential in this case, which we can remark by big D for the case of curve system, DAI, and which is will be this vector. This is DAI minus delta AI. Because AI will disappear and we will have only this one. So this is differential, please write differential in a curve coordinate system. So, and this, for example, this is normal. I can call it as a normal differential, and this is the part which appear due to the fact that this is not completely Cartesian system. And exactly this part, from this geometrical point of view, delta A can express through the Christoffel. On this, we can write that I can change index, but the idea like this, so this is minus gamma k I k l a a dxxl. So, or as a result, maybe it's only not important to write. Soon I need already to finish the lectures because I have a meeting. So what is important that we can see, and from this and from this, that if we have a Galileo reference system, all flat space, in this case, all Christoffel symbols, all components of Christoffel symbols will be equal 0. So, and in this case, we have the condition that covariant differential equal normal differential. So again, just to, because here I speak about derivative, this is derivation, differential. So if we will now to come back to definition of example for flat space. Okay, let's call it like this for flat space. We know that flat space. We know that dA equal I L dxl. Okay. Curve space. We write, you can see that now I put big D, dA equal A I covariant L dxl. So this is, you can see that why it's convenient to put here comma and here punta comma, because if you write the normal derivation and differential and covariant differential, so you can see that the formula looks like the same. The difference only here. But you need to remember that exactly this one is really different. This one means that we have dAI by dxl, but this one formula which we put here, so I can write it here. Repeat for this index. This y, this here. It means that we need to write a I equal the normal plus gamma a, and here I put the Christoffel symbol take all time these indexes, so I put here I. Here I need to keep L and summation index. So this one, okay. We also can find the same way which we found before. This way, we can find the formula and okay, this is covariant of covariant vector. If we will repeat the same procedure, we can obtain, and we will use it, the similar expression for the covariant vector. So for the covariant vector, we will have, and this will be your home task. So the home task, this is to prove that AI, and now we apply covariant derivative equal minus gamma k I L A K. And this is covariant derivative of covariant vector. So home task to prove this, to obtain this expression using the same procedure which we did here. Okay, so it will be some training, and you know, when you train, you write something by yourself, you understand better. If you will have some question, we can discuss. For today, and please, for this, I give time. It's very quickly to do. So please do it up to Monday, or the last point. So if I give some home tasks, I give usually 1 week. So 1 week up to the second Friday. The next Friday. Okay. Your home task, please, write if you want. After this, make a picture, make a PDF, and please send me by email. Email, you can send me on Gmail. It's even better. My email, bunny.k, gmail.com. Okay. So, and all home tasks which I give, you need to make it during 1 week. If you are not in time, and I don't want to receive at the end of semester of home tasks, please check everything. So please do it in time. And what I wanted to say also, that again, to remind that you can see again from this expression also that if gamma equals 0. So in this case, we this covariant derivative go to the normal derivative. So please some question, because I'm really need to rush now. I have the meeting and I need to be present there. Do you have some question? No questions?
No questions.
Okay, now I make a screenshot. So for the next lecture, we will consider the covariant derivative for tensor of the second rank and the expression through the metric tensor. And after this, we will work with Riemann tensor. Okay. In this case, good weekend and see you on Monday.
Thanks for lecture. Goodbye.